Good morning Year 9, and here we are back on distance learning, topic B4, and we're kind of halfway through the topic now because we're looking at our last lesson to do with photosynthesis in plants today. We're looking at transpiration in plants, and then next lesson we'll be moving on to the respiration part of the topic. So let's have a look at what we've got. So reminder from last lesson, the 5 uses of glucose in plants. So quickly, have a little sketch round of your hand, and in each finger I'd like you to write one of the uses of glucose in plants. Trying not to look back at your notes, try and get it from your memory. See if you can come up with all of those 5 different uses that plants use the glucose for after they've made it in photosynthesis. If you need a clue, here it is: scarf. Don't just write the letters, write the whole word for each of those 5 letters. Okay, if you need extra time on that, pause now. Today's lesson is how could we measure rate of transpiration? Okay, transpiration, and we write down our title now please. Transpiration is the movement of water from the roots to the leaves. It happens in those xylem cells, in the xylem tubes, and the water is absorbed into the roots through the process of osmosis, as we learnt in B1, and it moves just like if you were drinking through a straw. As soon as you drink some of the drink through the straw, more is drawn up, and that's exactly the way it works. So we've learnt about those stomata. The guard cells surround the stomata, and water evaporates through the stomata, and as it evaporates, more water is drawn up through the xylem, therefore through the roots, by this process of transpiration. So that's what we're going to investigate today, and I do say investigate because we're going to use the modelling program to get our results. So title: how could we measure rate of transpiration? Now, this is just a really simple idea of how we could measure that rate. So we know that water is lost through the stomata, through the leaves of the plant. An apple tree, kind of just a normal size, not a huge apple tree, will lose about a bathtub full of water every single day. And you can see here there's a plastic bag around these leaves, and you can see the water that's been collected in that bag, and that's all come out of the leaf. Okay, and then maybe something you saw at primary school, when we take a stick of celery and we put it in some food dye, it shows us that water moving by transpiration through the celery stick, and you can see all of those stringy bits of the celery. They are the xylem tubes. Okay, so that's where the water moves through, and it's taken the red food dye colour up into the leaves here. Okay, so those are just 2 kind of basic introduction ways that we can look at transpiration. Okay, another way we could measure transpiration, we could have a balanced set of scales here, and we've got our plant in its container. We could look at the mass of the plant. The water can't evaporate because there's this layer of oil over it, and then after a fixed period of time we could record the mass again. So we could leave this in a cold room for 24 hours and then look at the mass on the balance and see, has that allowed more water to be lost. We could then change that and leave it in a hot room for the same period of time, and then look at the balance and see what the difference is, how much water is lost in that fixed period of time. Okay, so you calculate the mass of water lost from the plant, and then you could repeat that at different temperatures or different conditions. You could have it in a still area where there's no breeze, then you could do it again in an area where there's lots of air movement. Okay, so this is one way that we could measure the rate of transpiration. If we could get some of those notes down into our book, please. If you need extra time, then pause now. This is the apparatus, the equipment that we're going to use today. It's called a potometer, and we've got this air bubble here, and we can put a ruler next to it, or they've got two markers, and that air bubble is going to move. Okay, so as water leaves or escapes through the leaf here, more water will be drawn up. It will be taken from this area here, and as a result, this bubble is going to travel towards the left. Okay, we've got this reservoir here, and we can turn that, and water will go in, which will push that back to the beginning for the second test. And we've got some water here to draw up so that we've got plenty of water going into the equipment. Okay, so let's look at our instructions for this. So we measure the position of the air bubble using a ruler, and then after a fixed period of time, so we leave it exactly the same way. Rather than looking at the mass change in this method, we look at how far that bubble moves, and then we calculate the water lost from the plant, and then we can repeat at different temperatures. The program that we're using today also allows us to change the number of leaves. So there's lots of different independent variables that we could look at. We're going to look at different temperatures, okay, and I think we're going to look at airflow as well. So we're kind of looking at two independent variables there. So both of these are really cool potometers, okay? It's spelled P-O-T-O-M-E-T-E-R. And the first one was a mass potometer. And this one, I just tend to call this one a potometer. Maybe you could call it a liquid potometer. Okay, if you need extra time, then pause now. So this is the equipment we're going to use. You can see we've got a hairdryer there. We can have it off, cold, warm. We can change the number of leaves. We can change the time. And then we've got this bubble, and we're going to see how far that bubble moves across the ruler when we do each of the different tests. So before we can actually get some data, we are going to have to get our table of results ready, and that is just here. Looks quite similar, doesn't it, to when we did the other investigations, the ones with the limiting factors of photosynthesis. We're also going to use this program one more time after today, and that's going to be looking at anaerobic respiration in yeast. Okay, so we are going to look at it. I will today put the link for you to use the program. If you would prefer at this point in time to have a go at playing around with the program on your own, that's absolutely fine. When you go into the link that I'm going to send you on Show My Homework, you just click on Scientific Investigations 2 and then Transpiration, which is in the AQA section, and you will see the program there. And you could actually just collect the results yourself if you'd like to today and put them in. That's absolutely fine, not a problem with that at all. Okay, it might be a bit more interesting than watching me collect the results, okay? But all these programs work in quite a simple way. Just play around with it. Don't forget to press repeat reading to get your 3 readings. If you just keep starting and stopping, you'll always get the same reading, so you do have to keep pressing repeat reading. Okay, so get your results table drawn, and if you need extra time, then pause now. So here we are in the program, and like I said, if you want to use the link on Show My Homework and get into the program yourself, get your own results, absolutely you can do that. You can see by your table of results what we're going to do. Number of leaves, I'm going to stick with 10 leaves. I could change that and have less leaves and look at how that affects it, but I'm going to go for 10. I'm going to go for a fixed period of time of 10 minutes, and you can see that is already changing. So this is with no air. Okay, so this is my first one, no air, and I can see, notice how at the beginning it's the left side of the air bubble that is lined up with the edge of the ruler there. So we always need to look at the left side of the air bubble. Do the same thing here, and the ruler is in reverse. So 1 is over here and 2 is here. So some people might jump in and say, oh, that's 2.2. It's actually 1.8. Okay, so I've got 1.8 for no air, test 1. Repeat reading, 1.7. Repeat reading, and we're back to 1.8 again. So no anomalies there. Next time I'm going to go for cold air, and my first result after 10 minutes with 10 leaves is 8.8. Repeat reading, 9.2. Repeat reading, 9.1. I use the edge of the bubble, it's called the meniscus, the outer curve, that's the bit we've got to use. And now we'll go for warm air. And we've got 18.2. Repeat reading. Oh, that's a tricky one. I'm going to go for 19.0. And repeat reading, 18.5. Okay, I'm going to go back to my results table, put my results in, and if you're using the program yourself, you can do that. And then we will start looking at calculating means and how we're going to present our data. Okay, so here are my results, and I've added the means. And remember that when we add those means into our table, we use 1 decimal place. Okay, the calculator may give you lots of information, but 1 decimal place is what you need, because all of your original results were to 1 decimal place. And that first mean came out as 1.76 recurring, and so I round that up and that becomes 1.8. My second result, even though it's just 9, I'm going to keep that to 1 decimal place by writing 9.0. And then my final result was 18.6. Now you may have different results because you did it yourself, that's absolutely fine. Use your results and calculate your means, okay? And if you need extra time for this, then pause now. I've now chosen to put my data into Excel. You can see I've highlighted these aspects again. I'll do it for you again. So I'm highlighting this part, then I press Control and I highlight this part, and I'm going into my charts and graphs, and I'm going for a bar chart, okay, because we've got what we call categoric data or discrete data, okay. We've got no air, cold air and warm air, okay. So I'm going to click that one, created my graph, same thing I did before. I'm going to go into add chart element, and I've got my axis title, the primary, the horizontal one there, I'm going to call that air condition, okay, so it's like the condition that the plant was in. I'm going to add another one here for the vertical axis, and I'm going to call that, and I've got it up here, okay, water lost by measuring movement of air bubble through the, it's a long one this one, the capillary tube in 10 minutes, and that was in centimetres. Now I've got one thing I can do there to kind of make that better, because if you remember we've calculated the mean, so I'm going to change that to mean water loss, and there we go. And I'm not going to bother with that chart title, so I'm going to delete that, so we can see the differences there, okay. If you're somebody who knows how to add error bars, give that a go. If you don't know what an error bar is, maybe you could look that up. I don't know how to do it on Excel, but we could have a look at that maybe when we go back into the original PowerPoint in a minute. So there is my graph of results. I'm going to take that graph into my original PowerPoint and we're going to chat through that now. If you can do it on Excel or you want to do it on Excel, then give it a go. If you're not that keen on that, you'd prefer just to do a bar chart in your book, also absolutely fine, okay. So I've now put my results, my graph there, my bar chart, into the original PowerPoint so we can discuss it. And we'll look through, first of all, the independent variable is the air condition, so whether there's no air, cold air or warm air. You could say that really we're looking at a couple of independent variables there, because we've got this idea of, is there movement, because the no air compared to air, and also the temperature of the air, the cold air or warm air, but we've kind of encompassed that and just called it air condition. The dependent variable is how much water was lost, okay, so we called it the water loss by measuring movement of an air bubble through the capillary tube in 10 minutes, and that was measured in centimetres. Controlled variables, we kept the same number of leaves and we kept the same fixed 10 minutes of time. So we can see if we describe the results that warm air resulted in the most water being lost from the leaf. No air resulted in the least amount of water being lost from the leaf. And if we look at it kind of roughly, we've got a bit of a doubling thing here. So cold air compared to warm air releases about double the amount of water that cold air does. So they quite like those comparisons to say double or 4 times or however many it is. Okay, here we've probably got about a 4-time increase from no air to cold air. And then it says explain in terms of particles the results. Okay, so when we've got to kind of think a little bit how we would in chemistry now. So when the air is warm, the particles have got more energy, so they're moving around more, and therefore they're more likely to escape from the surface of the leaf. When there is air, it's good at moving particles, okay? So when there's cold air, for example, or warm air, the air is causing those particles to be moved away from the leaf, but when the air is warm, you've got the addition of that extra energy, more evaporation coming from those leaves. Okay, and we talked about error bars briefly, and error bars are basically, they look like a small, in fact actually, I'll tell you what, I'm going to pause this, I'm going to add an error bar to show you exactly what they look like. Okay, here is an example of an error bar, and what this shows us is the range of our original results, okay, and this one, please be aware, is not to the results, okay, it was really hard to try and create this little error bar, so it's not to our results, but basically the bottom of the bar gives you the value of the lowest result out of the set of results, the value at the top gives you the highest value of the set of results, and then you have a bar in between, and it shows you the kind of variation between the results. We call them error bars, okay? So a big error bar shows that our results were very varied. A small error bar, we can kind of trust those results a bit more because the results were all quite similar. Okay, so that's something that you could add to your graph if you wish. Okay, last slide for today then. A quick 3-marker to finish our lesson. Explain why the mean rate of water uptake is higher on a hot day than on a cold day. So why is it that more water is taken up through the roots on a hot day than on a cold day? Okay, it's a 3-marker, so we need to give ourselves 3 minutes for this one. Try and give it a go. Don't just skip straight to the mark scheme, and to give that a go you need to pause the video now. Okay, let's have a look at the mark scheme then. So explain why the mean rate of water uptake is higher on a hot day than on a cold day. And because, as we've talked about and we've shown by our results, on a hot day more water is lost, okay, and we can say how that's lost. It's lost by either transpiration or evaporation, or an even better word is called evapotranspiration, which means movement of transpiration by evaporating through those stomata. And because more transpiration takes place, we talked about it being like a straw, more water will be taken up through the roots to replace that water. So 1 mark for saying that on a hot day there'll be more water lost from the leaf, escaping, and that's a result of transpiration, evaporation, or if you want to say evapotranspiration, and therefore more water will be taken up through the roots to replace the water that's been lost. If you need extra time doing your green pen, then pause now. And we've come to the end of our lesson today. Well done Year 9 for getting through to the end. We are going to look at respiration next lesson and comparing aerobic and anaerobic respiration in humans. Okay, have a good day, enjoy, and thank you.